Welcome back. This is part 2 of the series. If you did not get to watch part 1, go to the link in the description below. Let's continue. The Apollo Lunar Landing Training Vehicle, which debuted in 1968, marked the first instance of a purely electronic fly-by-wire aircraft without any mechanical or hydraulic backup. Preceding this was the Lunar Landing Research Vehicle in 1964, another pioneering example of fly-by-wire flight that relied solely on a digital computer with 3 redundant analog channels. Concurrently, the USSR's Sukhoi T-4 and a modified trainer variant of the British Hawker Hunter fighter in the United Kingdom also employed early fly-by-wire controls. The first fully digital fly-by-wire fixed-wing aircraft without mechanical backup took flight in 1972, when NASA electronically modified an F-8 Crusader as a test aircraft using Apollo guidance, navigation, and control hardware. The Airbus A320 entered commercial service in 1988 as the inaugural production airliner equipped with fully digital fly-by-wire controls, introducing the concept to civilian aviation. Airbus pioneered fly-by-wire technology for commercial airliners during the 1980s, prompting widespread adoption by major manufacturers over time. Boeing adopted fly-by-wire flight controls for the 777 in 1994, departing from traditional cable and pulley systems. Fly-by-wire eliminates traditional mechanical linkages, enhancing aircraft reliability and reducing maintenance costs compared to conventional controls. Moreover, in designs with limited relaxed stability, such as the Boeing 777, fly-by-wire systems enable more efficient flight profiles, optimizing both operational costs and fuel efficiency. Fly-by-wire flight control systems replace the complexity, fragility, and weight of mechanical or hydromechanical flight control systems with electronic circuits. Cockpit control inputs are converted by signal transducers into electronic commands processed by either analog or modern digital electronic controllers, which now also integrate aircraft and spacecraft autopilots. In early analog configurations, hydraulic circuits use electrically controlled servo valves operated by the electronic controller, which also manages feel forces on manual controls to simulate feedback, as seen in the Concorde, the pioneering production fly-by-wire airliner. Digital fly-by-wire systems expand upon analog counterparts by employing digital signal processing to interpret inputs from multiple sensors simultaneously, such as altimeters and pitot tubes, adjusting controls in real time. Flight control computers receive and analyze position and force inputs from pilot controls and aircraft sensors, solving differential equations to generate precise command signals that align with pilot intentions. Digital computers in fly-by-wire systems enable flight envelope protection, tailored to the aircraft's handling characteristics to ensure it operates within aerodynamic and structural limits. This includes preventing dangerous maneuvers like stalls and spins by limiting control inputs and stabilizing flight control responses to mitigate pilot-induced oscillations. Continuous feedback from flight control computers reduces pilot workload and facilitates enhanced maneuverability in military aircraft with relaxed stability. This capability, known as carefree handling, allows for safer and more agile performance in combat and training scenarios. Digital flight control systems are crucial for inherently unstable aircraft like the Lockheed F-117 Nighthawk and Northrop Grumman B-2 Spirit, enabling safe and effective flight through precise control and stability augmentation. Reliability remains a paramount concern for digital fly-by-wire systems due to their dependence on software. The failure of flight control computers can severely limit pilot control, necessitating robust redundancy measures. Therefore, most fly-by-wire systems incorporate triple or quadruple redundant flight control computers operating in parallel, ensuring continued operability through multiple independent data buses connecting each control surface. Perhaps the most impressive features of fly-by-wire systems are their built-in protections: roll protection, yaw protection, though differing slightly between the 787 and 777, overspeed prevention, stall prevention, and more. These safeguards form a comprehensive safety net. Feeling adventurous enough to push the limits? The system will intervene, preventing maneuvers that could compromise safety, such as trimming up to the point of stall. Want to perform aerobatics like Tex Johnson? Simply deactivate the bank angle protection first. However, these sophisticated protections are mostly or entirely disabled if the system automatically switches to secondary mode or if the pilot manually switches to direct mode. Additionally, the autopilot functionality ceases in these modes. The multiple redundant flight control computers continuously cross-check each other's outputs. If one computer detects anomalies due to software glitches, hardware failures, or erroneous input data, the system disregards the affected computer's outputs and relies on the consensus of the remaining computers. Procedures may include rebooting the aberrant computer or reintegrating its inputs once they align with the others. Complex failover logic ensures the system can manage multiple failures, potentially reverting to simpler backup modes if necessary. In earlier digital fly-by-wire aircraft, there typically existed analog or hydraulic backup systems alongside the primary digital controls. For instance, the Space Shuttle employed a fifth backup computer, distinct from its primary set of 4 digital computers, ready to assume control should all primary systems fail due to unforeseen software faults. Actuator control electronics are responsible for transmitting signals to adjust control surfaces, while primary flight computers receive inputs from actuator control electronics during manual flight or directly from the autopilot system. Primary flight computers process these inputs alongside inertial, air data, radio altimeter, and engine control inputs, generating refined signals transmitted back to actuator control electronics and then to the control surfaces. The redundancy of having 4 actuator control electronics and 3 primary flight computers enhances system reliability. Despite this redundancy, some controls in the Boeing 777, like certain spoilers and the stabilizer, retain conventional backup methods. In contrast, the Boeing 787 relies solely on its advanced fly-by-wire system without such traditional fallbacks. In the event of sensor failures or other anomalies, the system switches to secondary mode where primary flight computers continue to process data, albeit in a simplified manner, using remaining or older data. If all primary flight computers fail, a rare occurrence, or if pilots manually disconnect them following established procedures, the system reverts to direct mode. In direct mode, pilot inputs bypass primary flight computers and directly command actuator control electronics, which then control the surfaces. Please leave a like and subscribe to us. It will help us greatly in creating interesting content like this for you, and click the notification bell so you won't miss any future videos when we post new content. Airbus and Boeing take distinct approaches in implementing fly-by-wire systems in commercial aircraft. Since the Airbus A320, Airbus has maintained a flight envelope control strategy where ultimate flight control remains with the automated system under normal law. This ensures pilots cannot exceed aircraft performance limits unless deliberately switching to alternate law due to system failures. On the A320, mechanical backups exist for pitch, trim and rudder, while the A340 features an entirely electrical backup system for its rudder. Starting with the A380, all Airbus flight control systems incorporate a 3-axis backup control module, BCM, for electrical redundancy. In contrast, Boeing aircraft like the Boeing 777 empower pilots to fully override the computerized flight control system, enabling operation beyond normal flight control boundaries if needed. Fly-by-wire systems eliminate traditional mechanical transmission circuits, and further advancements replace heavy hydraulic circuits with electrical power circuits. These circuits supply energy to electrical or self-contained electro-hydraulic actuators controlled by digital flight control computers. This transition maintains all the advantages of digital fly-by-wire while enhancing weight savings, allowing for redundant power circuits, and facilitating tighter integration with avionics systems. Eliminating hydraulics also significantly reduces maintenance costs. This technology is utilized in the Lockheed Martin F-35 Lightning II and Airbus A380 backup flight controls. Additionally, Both the Boeing 787 and Airbus A350 incorporate electrically powered backup flight controls that remain operational even in the event of a complete loss of hydraulic power. Thank you for watching. See you in the next video.